First and foremost, can everyone see my screen? You should see the slides, and then you should see black borders on the sides.
Yes.
Okay, cool. I'm going to assume the one person's going to speak for the rest of you. Excellent. um, anyway, I'm going to talk about building custom hardware for the Intel i960Sx series of processors. This has gone on for several years. It started in 2018 and has been evolving ever since. So we're going to talk. I'm going to give you a little motivation of why I'm doing this. We're going to talk about the designs and where I'm going to go in the future. So the first question is, what is the i960? Well, it was a RISC processor designed by Intel in the 1980s as an offshoot of their failed 432 processor. It has a clean 32-bit flat memory model, a very elegant instruction set, and you may have actually used these processors if you've flown the F-22 Raptor, or you've played games like Daytona USA in the arcades. Also, it's been used in many, many slot machines from IGT and various RAID and network cards. And there's at least one DSL modem I know of that uses it. So the model of the i960 is really cool. It's very, very simple. I have on the right over here is the actual, it's taken from the data sheet. It's very clean. There's no IO spaces, none of that. You get access to 32 general purpose registers, 16 globals, and 16 local registers. They're all 32 bits wide. And if your i960 is equipped with an FPU, you get 4 80-bit floating point registers as well. It has a very, very well-defined data type system. And this is a subset. You have ordinals, which are unsigned, integers, which are signed, and reals, which are floating point. And there are several registers, at least 3, I know off the top of my head, that have fixed purposes. And we'll get into what those are. But the first thing I want to show is the instruction set. What you see on the left is the entire instruction set. Now, there are variants of some of these, like add also has an ordinal and an integer and a real version and various things, but they fit on a single page like this. To the point of the core instruction set does not include the decimal, the conversion, or the floating point operations. So it's even smaller in its core set. Decimal is used for branch, for BCD, because remember, this is the 80s. But it also has some really cool sets of logical operations that I've not seen in any other processor, like not and not, those are different. NAND, exclusive NOR, not or, and or not. Those are my favorites. It also has some really cool functions that I usually have to write by hand in C and C++ that called extract and modify for bit manipulation. But the really cool thing is the call and return system. And the other neat thing is you can do floating point operations in normal registers. You don't need to swap all your data over to floating point registers and do all sorts of weird shenanigans to get it to work. You can just say, here, interpret these bits as floating point numbers and add them. And you can even mix them with those 4 80-bit floating point registers. So it's really neat. But the other neat thing is this function call mechanism. So when you do a call in this architecture, you are actually doing quite a few things. The local registers, the upper 16 of your 32 register set, is local to your current function. So when you do a call, whatever registers were in those locals are moved into another frame, and you get a new frame to write your own locals to. So you never have to save and restore registers, except if you're messing with the globals. So code can be much more compact and concise. This is not the only chip that does this. Spark does this too, and a few others. But the design is really cool as well, so that you're not going to have an infinite number of these register sets on chip. So when you run out, in the case of the i960S series, it's 4, but it can be any number. When you run out, the processor will automatically spill those register sets to main memory inside of the stack frames it sets up in hardware. So you don't have to worry about, am I going to overrun things? There's already memory set up for it. And there's even an instruction you can say, no, just dump the cache to main memory for, like, just do it. So it's really neat. Really and truly, I really like the programming model of this chip. It's really, really elegant. As I stated, you can mix GPRs and floating points together, which is really cool. And it's the only chip I've found where there's a book, and I have it, that describes why they made the choices they did, not just this is how it works, which is very, very rare. And I do actually have access to GCC and bin utils for this. It's very old, it's GCC 3.4.6, but at least I have C++. Not 11, but that's fine. So I'm like, okay, cool. Let's build some hardware. Let's build a main board for this. So I need to choose a processor. I would like to have a floating point unit just because that's really cool to have. I need to make sure the CPU package can be easily installed or replaced without risk of damaging the CPU or the socket. And I'll get into what that means in a little bit. It needs to have a complete data sheet because there's no way I'm going to just start applying power to random pins to see if it works. That's a real good way to start a fire. So that's not going to happen. And if I have extra reference manuals, that's a bonus as well. I'd like new old stock, if at all possible. I don't want to have to go and trying to extract this off of old hardware. It's not going to end well. I'm not going to buy tons and tons of laser printers from the early 90s to do this. And the processor must run at either 3.3 volts or 5 volts. I don't want 7 volts. I don't want 9 volts. I don't want any dumb things from like the 80s. I want it to be very easy to interface with. But here's the realities. These processors are no longer made. Intel stopped developing them in addition to all their other lines in about 2007. It's not totally true. There is a company called Rochester Electronics, and they do make the military versions, which are made with ceramics, but they're $1,500 a processor. And I don't know if I'd be put on a list for trying to buy military hardware. So even if I wanted to go down that route, and I don't. But this place does sell new old stock of some of this S series processor. There's a finite stock of them, but I was able to source about 22 of them. And the other problem is a lot of manuals and source code are lost to time. A lot of it was scanned, but I have worked with a lot of people over the last 3 years to get more of it visible. Like it's more like islands of data, but there's a lot of stuff that's just lost to time. So the outcome of all of this research, which I have just condensed down what probably took about 2 or 3 months down to this very minutes. I chose what's called an i960SB10. As I stated earlier, I was able to source 22 of them. It does have an FPU, which was one of the big things. This is the A variant, which does, what you're seeing on the left here is the A variant, which is 16, which means it's supposed to run at 16 megahertz. The 10 means it runs at 10 megahertz. You can run them as low as 4, but I don't trust that because I've gotten different answers from different data sheets. And I'm like, I'm not going to, I know it's supposed to run at that speed. So we're going to run it at that speed. And it uses what's called a PLCC84 package. These things are used everywhere. They're easy to find. And I have a pull tool that I can use to I can pull the chip out really easily and replace them. And the thing runs at 5 volts. So this is going to be the easiest one to use. So let's talk about what this package actually looks like and what we're going to have to do. So there's a large number of power and ground pairs. I don't know if you can see it on this 84-pin package, but there's a bunch of these VSS and VCC groups. And these are power and ground pairs. And according to the data sheet and the manuals, the reason why there's many of them is because each one powers a separate functional unit inside of the processor. Their logic being that it makes it easier to do power management and they don't have to spend as much real estate inside the chip to handle this. So you can do it externally and have a better time. Sure, okay, good to know. And that'll become important later. If you shouldn't ignore that. Several pins are marked no connect. So even though it's in an 84-pin package, there are, I think, 4 or 5, maybe even 6 of these along the edge. You'll see the same NC, and those don't need to be connected. So cool. And then there's 32 pins devoted to an address and data lines. We'll get into that. Yeah, we'll get into that. And then the rest of them are control signals. So we have a processor, and now we need a way to actually interface with the processor itself. I can't just, I could solder to the legs, but that's a bad idea. We need an interface board of some kind. So there's some necessary hardware, and this is what the rest of the talk is going to be about. I'm going to go through my adventures in making an interface board, demultiplexing hardware and demultiplexer, and the chipset. You can't see my hands right now, but I'm doing the quotation fingers for chipset. So the interface board is the first thing that I had to make. And so, as I stated, you need a way to interface with the CPU. I've gone through 8 revisions of this board. I started with the electronic design tools fritzing, but I moved on to KiCad because fritzing kept crashing the more pins and traces I added. But let's start with the first interface board. And no, I'm not going to go through 8 generations of this. I'm not going to subject you to that. But I am going to show you the first one. So as you can see in the center here, you're seeing the top and the bottom of the board. And in here, this is the PLCC socket right here, the giant square. And you'll see on the left, there's a bunch of breakouts for all the control signals. Here's some control signals up here. Then you have data lines and address lines. I will just say this thing was designed with naivete in mind. But there is one thing that you may have noticed. And this is why I was saying earlier, you don't want to ignore the separate power and ground pins. So what are we looking at here? Why is there this giant black spot? They normally don't put what looks like this in manufacturing. Okay. So this was my fault, but I learned a lot from it. So the processor needs about 200 to 300 milliamps, and my little breadboard power supplies could not supply that current. You'd power on the processor, and the entire thing would shut down. So I had the bright idea of taking a power charger meant to charge USB-C laptops. So they should do, it's like fast charge. It's great. It won't dip or anything like that. But it also has USB-A ports. So I plugged that in, used like a little USB voltmeter, and plugged that into the breadboard power supply. Not only did the processor get unbelievably hot, which was weird because the data sheet said it shouldn't do that, it started to burn underneath the solder mask, and that's what these black marks are. If you look really closely on the top, you can even see the exposed copper of these traces. It's not supposed to do that, not at all. And it makes the most wonderful burning smell, so I may have actually reduced my lifespan when I did this. But either way, the other problem too, and the reason why it shows up like this on both sides, is because I was putting 2 amps through this tiny, tiny little trace, and there is a right angle in here. And what that does is the electrons come across and they impact the corner and then bounce over, creating friction and creating heat. So the more that goes through this tiny little wire, the more it heats up and started to burn the solder mask. I have never done that since. So let's talk about some of the other challenges besides, burning the thing underneath the protective layer. You should definitely decouple all these power lines into separate locations. All these power and ground pins must be separated and decoupled with capacitors, so that if there's power dips, the capacitors can basically provide enough power until provide enough backup voltage so that it doesn't, kill the processor and like shut down. You'll notice on the board there was a single resistor. That's because there's a lock pin, and the little tilde means you set it low to engage it. The lock pin is open drain, so you can wire it into other main devices on a bus, but it needs to be pulled up to prevent basically erroneous operation. The through-hole PLCC sockets are awesome, but you have to use really fine traces to work correctly. And you need to use something called ground and power planes. And what this is, instead of having that single little wire you saw, you instead, you take available space on each side of the board and you turn it into a plane of copper that is wired into a given pin. So on the top, I may have power, so the voltage would go through this entire area of the square. and then on the underside it would be ground. Not only does it make it less likely to burn, it also provides thermal, it also distributes that any sort of current across the entire area, so it'll cool it much faster, it'll cool it in a better way. The only downside is that if you have a lot of traces, you may have to start getting really creative and start having to use vias to worm your way across the board to have consistency. The other nice thing is I learned how to do surface mount soldering for the capacitors, because doing through-hole capacitors on this makes it really hard to route all the traces. But with everything I learned and all the revisions I went through, this is what I currently have. I apologize for the light, basically the flash here, but this board is a 4-layer board instead of the 2 you saw previously. These larger gold plates are for capacitors. Here's your resistor area. And you'll notice here I have the breakouts for the address lines and the control signals for that. You have some holes here. Unfortunately, I didn't gold plate them yet. I will eventually. I don't want to be NZXT and put out a product that could cause a fire, but I'm not worried about that right now. But you'll see I have all the other control signals broken out on the other side. It does work. The inner layers act as these ground and power planes, and the top and bottom layer that you can see are for the traces. But because all the pins, the interface with wires are on different sides, you start to run into problems where basically, if I was smart, I would have put this all on one side, but it makes the board longer and technically more expensive. When you're getting these things made, there's a bunch of the design guidelines from who you get it made from spell this out. I also added down here, this is a power LED, just so I know the thing is working and I have power applied to it. So we have a board and I know this thing works. Now we need to demultiplex. As I showed here, there's these 2 blocks of double road pins, and we're gonna talk about this. And this is probably the worst part of this entire thing. I hate this, and this took about 6 months to figure out what's going on because I have no electronic design background, so I'm learning this on the fly. So Intel kind of got a little cheap when they made used the PLCC84 socket. The upside is it's a very common socket. It's very easy to use, but they don't have enough pins being exposed in the processor to have separate address and data lines. So instead, they multiplex the lower 16 bits of or the lower 16 pins, I should say. Because of that, you have to have extra external hardware to perform the demultiplexing. And I finally bought a physical copy of the i960Sx K-series hardware designer's manual, which is the full 32-bit bus version of the S series. So nearly everything applied. Yeah, so on the right here is the parts of my schematic that I had to use in order to demultiplex the signal. So you use 2 transceivers, which you can set the direction, because these data lines have to operate as both input and output. And then you need to separate the address, the lower 16 bits, from the address. Well, it's actually 15 bits because you always operate on 16-bit. It's always a 16-bit address. You always load 16 bits, so A0 is not defined. I'll get into that, how I hacked this later. But so you have these data lines, but the address lines need to be saved, because the way this works is first the processor sends out its full 32-bit address, and then it switches through these 3 control signals, ALE, DEN, and DTR, to saying, okay, now you can use these as data. So once you have this discrete hardware, you're ready to go. You can't really use a microcontroller for this because the microcontroller is too slow. So yeah, so I have this thing set up, and this is what it looks like. This is the render of it. I actually have it sitting on my desk here. And so what happens is that these 22 pins, you hook this up to the interface board, and then the transceivers and the latches are used to store the address, go here. These are the latches, and these are the transceivers. And then you get 32 pins out. And I provided an A0, which is always low because as all operations are bound to 16-bit boundaries, just so that it is consistent. So we have this hardware now. So cool. We've broken it out. Awesome. But we need a way to make a bus out of this. So I need to make a chipset. So I don't really want to sit there making discrete hardware for the rest of my life to do this, and potentially having to find stuff that's been discontinued for 15 years to assist me. So let's just use modern stuff, and we'll just, like we do, like people do with a lot of projects these days, let's use Arduino. So I have a Atmega 1284P that has 16K of SRAM, 128K of flash. I can run it at up to 20 megahertz, and it operates at 5 volts. I have 32 input and output pins I can use from the process, from this microcontroller to do things. And it will be responsible for providing the CPU a clock source, handling all the memory requests, timers, if for some reason I want it, the chip provides it. And I can interface with modern devices like Bluetooth and Wi-Fi through it, and provide access to external memory sources. So this would be the ultimate controllers, and it's really cool. Oh, and you may be saying, oh, 16K and 128K of flash. Ooh, that's really, really low. How are you going to do anything? Well, a lot of microcontroller projects use what's known as a Atmega 328P, and that has 2K of SRAM and 32 kilobytes of flash. So this is like much higher. This is a much higher end chip. But there's a problem. I have 69 pins I need to interface to the chipset, but the chipset only has 32 pins. And 32 is obviously less than 69, and I can't just shove pins together. It doesn't work that way. But it gets worse. I don't get access to all 32 of those pins. One of them is devoted to providing the clock source. Another one is for the Arduino serial console, so I can debug things. I need access to SPI, which is a protocol. Another one, I need access to another one called I2C. I want the AVR interrupt pins free. So there's 3 of those. So at the minimum, I've lost 12 pins. So now I have to try and bind 69 pins to only 20 free pins. So how the hell are we going to do this? This is a real classic problem in embedded design. And even if I ignored the address and data lines, which would give me, it would subtract 48, we would still have 21 pins we need to work with. So this is where SPI comes in. And SPI is a serial protocol where instead of sending out all the bits in parallel on separate lines, you clock out each bit individually. So it's slower, but it's infinitely more flexible, and you can connect many devices to the SPI bus. These 4 pins here, PB4 through PB7, this is a hardware SPI controller that's built into the microcontroller. You can add more control, like chip select lines to control more devices, but for what we're going to do, which is GPIO expansion, we only need 1 pin to control up to 64 pins. So we need to be able to read all 69 of these lines. So how are we going to do this? Well, we're going to use something called an MCP23S17, the most understandable name in the world. It is an IO expander chip that provides 16 input and output bidirectional pins that are programmable, and it has the ability to bind up to 8 of these to a single chip line. So with just 4 pins, we can control 8 of these. It has a maximum speed of 10 megahertz, which is very high for this, and we will never achieve it, but it's not important. But the concept is we use 3 of these expanders to handle the address and data lines, and we convert them into serial streams. We use an extra pin microcontroller will provide an extra pin for the reset pin on these IO expanders. That's important for when you boot up. You want to make sure it's not in a garbage state. But 2 of the 3 of these devices will be configured purely for input and never be changed. And the data lines, which are 16 of them, it's almost like that. I thought like I chose that because of it, can be configured by input or output based on other control signals. So this is what it looks like in practice. So you'll see here I have 3 of these guys. They're hooked into boards. And they're all, you can't see it here, but they're all hooked into the same 5 wires. And then you'll see here this just massive wires coming in. And I don't remember the order I put these in, but generally it's going to be 2 of these will probably be, well, no, they will be. These are going to be your address lines, and this one would be your data line. And underneath here, these lines that say A0, A1, and A2 are what you do to bias the address. So this one would be 000, 100, 010. So they all have unique IDs, and you can actually tell the command you send which one you want to send it to by including this ID. So we're still not done though. So we have 5 pins that handle 48 address and data lines. We still have 21 pins remaining from the processor, but we only have 20 to use. So what else can we do? Well, we need to save more pins. And I will say that there are other microcontrollers that have more pins, but I like this microcontroller, so I'm going to stick with it. So is there any pins? So the first question is there any pins we can ignore? And yes, it turns out according to the datasheet you can. There are 4 interrupt lines to provide. You can have 4 different sources of interrupting the processor. Well, our chipset only needs 1. So we can get rid of 3 of these, and we can bind them to other things or leave them unmapped. And these, like int 2 and int 3, have special uses if you're going to use an external interrupt controller like the 8259, which, no, I'm not using that. So we can just ignore these 3. So great, we're down to 18, but I'd like to save some more pins so I can control other external devices like Bluetooth, SD cards, RAM, external SPI RAM, etc. So we can add a 4th I/O expander. And according to the datasheet, there are 7 pins that we can move onto this I/O expander because we don't need direct access at any point. So the multiplexing gets even stranger, where the lower 3 lines are actually not multiplexed, but they are multiplexed. I don't know why Intel did this, but they did. So if you want to do burst reads and writes, you use these 3 extra address lines, and then combined with some other signals, you can quickly write and read large swaths of data. But we don't need to directly connect that to the processor. I mean, we're not connecting the address or data lines. So why would these get special priority? So, okay, these are always going to be inputs to the chipset. So we'll just put them on this I/O expander. There's also this other line that's called ALE, which we don't really use outside of the demuxer. And I don't know if I'm going to need it. So we'll just bind it to it as well. Same thing with another signal called address state, which I find absolutely useless because I don't need to know if I'm in an address state because I have the chipset, and the i960 will help you in a way. I'll get into that. There's also 2 other signals called byte enable 0 and byte enable 1. And this is used to specify which part of the 16-bit value being read or written is which parts you want. So if BE0 is low and BE1 is high, that means you only want the lower 8 bits. And if BE1 is low and BE0 is high, you only want the upper 8 bits. If they're both low, you want the full value. And if they're both high, you don't want any value. I don't know if the processor will do that. I don't know why it would do that, but it's there. And there's no need to do direct pin access for that either. So, so even with that, now we have 4 of the 8 total we can bind to that single chip select pin. And so now we're down, we've eliminated or remapped 10 pins. We only need 11 pins on the chipset itself to handle all this work, and we have 9 pins free for extra features and functionality, which is really nice. So that's really cool. And with that, now I'm like, okay, we have the wiring done. And obviously someone may come up with a different way you could do this, obviously, but this is what I found to be the best trade-off. But the next question is, we need to provide, is that the i960 is a synchronous processor, and you need to provide it with a clock signal. Obviously, I could get a 20 megahertz crystal and just hook it up to it and call it a day. And I did say 20 megahertz, even though this is a 10 megahertz processor, and I'll explain why I said that. But the problem is then I need to have a separate clock source for the chipset. So the clock signal is a little interesting on the i960. The pin that you input, the pin that takes in the clock signal is called CLK2. There is no CLK1 because it actually stands for clock times 2. So what happens is you provide a clock source that is double the rate of clock. So I need to provide a 20 megahertz clock to get a 10 megahertz signal internally. And if you can look at the graph on the left, you'll see that what's going on is as I understand it, the signal switch going this way and then going up, like in between this block here, represents an actual internal processor signal switch. So that's why it's wider. But I don't want to have two clock sources. That's ridiculous. So what I found was that you can program the fuses on the 1284P to force B1 to become a clock output pin. And so it will take the clock source the microcontroller is using and output it. So now I have the same 20 megahertz signal that's powering the chipset will power the i960. That's awesome. And I should also point out, you cannot single step these processors. A lot of modern CPUs, you can actually like stop the clock and it will work just fine. You cannot do that here. If you attempt to do that, it will completely hose the state of the CPU because it will lose all of its capacitance. And this is welcome to the 80s and the 90s, where you had to get like a giant extra debug probe processor that cost about the chips here for these i960s are like 20 bucks or something right now. The probe that I found for not even the S series was like 800 bucks on eBay. And I would probably have to use DOS and Windows 3.11 to interface with it. No, that's ridiculous. So we'll figure that out. We'll figure out how, if we want to single step debug it later. But there's another issue. So even though you have a clock signal, you also need to tell the i960 when it can, when it's ready to do the next memory transaction. But how do we signal that? Signal this readiness? Well, there's a ready signal or a pin from the processor called, well, ready. And you pull it low for a single clock cycle. So it's very important during read and writes, and it needs to be exactly one clock cycle. If you don't do this, you'll get really funny results. Having the microcontroller attempt to do this took microseconds when you're dealing with nanoseconds. So it totally failed the processor out because it said, oh, I'm still ready. Okay, I'll just keep reading what's already on the lines. Way too slow. So this is where I currently am having issues with, but you can see on the left how it's supposed to go. That like for this exact clock cycle, it's supposed to be low and then immediately come back. And this is where, I haven't solved this yet, but this is where it needs to go next. I have to use some discrete hardware. When you're dealing with the 8080, like the Intel x86 processors from the 80s, they have a chip that's called an 8284. And it handles most of this synchronization for you. But the 8284 is a little insane because Intel didn't do a divide by 2 clock signal like you saw. They did a divide by 3. I don't know why, but they did. So I can't just use this chip. But what you see here is the layout and the design that I got from the data sheet for the 8284. So I want to emulate this, but change the divider to 2 instead of 3 here. And so I'm working on that right now. It also has bits and pieces of it called a once and only once detector has to be in there, and something called a falling edge detector. I learn something new every day on this, but if I'm successful, then it should be clocked correctly to only fire once and then come back up, regardless of how slow the chipset is. So that's where I am right now, and where are we going next? Well, I have designed a new interface board that integrated those serializers and the demultiplexing hardware onto the same board. I want to get the ready signals working, and I want to provide simple programs to the i960 to execute, and then I want to figure out debugging. I have written an i960 simulator that will work, that's meant to be a full and emulated environment of a custom processor I've made called the Z series. It doesn't exist, it never existed, but it gives you the maximum design. That's going to use a ARM processor and run at 3.3 volts. It's using something called an Adafruit Grand Central M4. But I put that on hold because I figured out, I figured how to keep going with the ready signals. But the CPU provides something called once mode, so you can hook into the bus and it tri-states things. It was confusing. So that I have some ways to move forward if I need to debug in the future, but I'm not worried about it right now. So this is what the thing looks like right now. This is not the chipset I'm going to use. This is an older device called a Mega 2560, and it works, but I cannot provide a single clock source. The clock on this one runs at 16 megahertz, so it would provide an 8 megahertz clock to this, which is safe, but at the same time, I want to run it at 20. So and I would break the board if I tried to desolder the crystal out of here and reprogram it. It's just not worth it. But I don't like all these wires. I have to sit there and painstakingly connect them, and it's just awful. So this is the board I was talking about that I have been made. Once again, I'm still like NZXT, and I haven't properly plated these yet. But I'm not worried about causing a fire because I'm not going to put 12-volt lines near this. But yeah, so these 3 chips here, those are the serializers. Here's the demuxing hardware, and here's the socket for the chip, and here's the breakout lines, and here's the serializer breakout lines. I swapped the design so that all of the traces are on the inner 2 layers, and the ground and power planes are on the outer layers. I did this because I watched something about, I watched a YouTube video from an ex-Atari engineer who stated that they got around a bunch of FCC problems by putting all the traces of a 4-layer board on the inside and using the ground and power planes on the top and bottom layers to combat radio emissions. It still hasn't come in yet, but that will arrive tomorrow according to my tracking information. And so that's it. Does anyone have any questions?
So I was wondering why you picked such an old processor as opposed to some newer one.
Because I found the architecture extremely interesting, and I looked at it as a challenge. It's a very good question, but and so there was the challenge of it, and the instruction set was just so clean. I'm like, no, I want to make a single board computer out of it or something close enough to it.
So it's mostly just because you were interested in how.
Yeah. There is no practical application for this at this point in time. I mean, I can't get a C++17 compiler. I'd have to port LLVM or GCC to the chip again, and that's easier said than done. So there's a whole bunch of stuff that impedes me, but it just is pure interest.
So what are you hoping to get out as an end state?
Well, if I can run Doom on it, then I will consider it successful. I'm serious. I'm dead serious. And if I can connect it to the internet.
Okay, that's where you're hoping to go. Okay.
I actually have the devices. It's called an ESP32. You can get them as a breakout board, and it can communicate over SPI, and it provides Wi-Fi connectivity. So I can actually map that into the i960's memory space once I get to that point.
Cool.
Yeah, I also had a question. Maybe I missed this, but didn't i960, well, usually when Intel makes chips, they make a whole line of chips. I was surprised that they didn't make a separate multiplexing chip for this.
I am too.
Is that correct?
You are correct. They did not. I have many, many physical manuals, and they all say, here are the equations for the programmable logic device, so you can use it. I, to this day, do not know why. Even the development hardware that I bought off of eBay, they use an FPGA to do this. It's very strange. I don't know why they didn't decide to make like an equivalent to the 8284 and such. I don't know.
Do you think it will be easier and more efficient to make a multiplexer with an FPGA?
Yes, but I have to use 5-volt tolerant FPGAs, so there's much older, and a lot of them aren't supported anymore. I actually looked into that. It was not.
So they are 3.3 now, right?
Yeah, 3.3, yeah. And I have a bunch of chips that allow me to do basically bidirectional logic level conversion automatically. but they will slow everything down. I'm not really caring about speed, but that is something to keep in mind when I do it. So, and a lot of those chips are very expensive of the size I would need. They would require, like, some of them were like $200 like just for the processor, not including, like, for the FPGA, not including the programmer. I was really surprised.
Did I understand you correctly that you've found problems getting those chips?
Nope.
Well, I just looked at the DGK, and they have hundreds of
Yes.
80 and 960 ones.
Yes, because when about, I don't know, in the middle of 2020, Rochester started selling all their stocks on DigiKey. I bought them before that started happening.
I see.
So yeah, I saw that. I'm like, well, that would have been nice to have. That would have been really nice. But yeah, I bought a bunch of stock of processors from DigiKey as well, of i960 stuff. So the person who probably has been clearing out their inventory is probably me more than anyone else.
Any other questions? Comments? Anyone want to buy one when he's done?
I'm not going to mass produce it.
Well, I think that's
I was
it.
gonna say, are you gonna produce like even a limited run of it?
Well, I'm going to make boards for myself, yes. And when you get a manufacturer, they come in groups of 3. I'll probably open source the single board design when I'm done.
Can I donate to your Patreon to get one, or
Well, just what's the minimum bid
mass
price?
drop GoFundMe?
What's your minimum bid price on eBay going to be?
Oh my God, I haven't even thought that far ahead. I to be honest, I don't have an answer at that yet.
Is it more expensive or less expensive if someone gets to watch a video of you making it when they hit the buy
so
now
if these so the problem is the stocks of the S processors. So I actually bought 2 sets of them. One of them got lost in shipping. So 20 of those processors are sitting somewhere. I don't know where. So I had to buy a second set of 22 of them. And the stocks of them are limited. You can get the A variants that don't have the FPU in them, and those are much more plentiful. But to get the ones with the FPU in them are very, very, very limited. So I never even thought of potentially selling them. I don't know how long it will take to even, because I still have to get software up and running, because the monitor ROM, I have the access to the source code, but it's old KNRC, and it's really gross. And I have to make files written for DOS. So that's a good question. Maybe at some point I will, but I don't know yet. I'm not ruling it out. I just not at that point yet.
Is there any particular reason why you choose to use 3 boards instead of 1? Are you running out of layers on your PCB? Is that why?
So I used a 4-layer board so that I could. So if I'm using surface mount components, which in this case I'm mostly not, but when you use surface mount, those other 3 layers, so you can only put surface mount components on the top and bottom layers, but the middle 2, you can use those in order to jump around and dodge basically components. If you're using through hole like I am, because doing the surface mount PLCC sockets are awful to solder, even with a heat gun, which you do have. Because you end up melting the socket if you don't know what you're doing. It wasn't so much that I ran out of layers or anything like that. It was more that I needed enough space to put the ground and power planes in. That was the real reason.
I see.
How long before we get to play Doom?
I may end up actually using a Raspberry Pi for that, where you plug it into a Raspberry Pi and there's your GPU. I don't know yet. I'm still thinking about how I'm going to do the graphics processor part. I do have stuff that will work for 3.3 volt, but not 5 volts is the problem. I actually have something called a game Duino that I technically could use, but it operates at 3.3 volt, and I don't want to fry the thing working at 5 because it won't. It will just damage it.
That's kind of a joke question, but thanks for answering it anyways.
You're welcome.
All right, well, if there's no more questions, I think we're done. So thanks, Josh. That was great. I'll send the video
Yeah,
out.
thank you,
Anyone wants
Josh.
to watch it again?
Can you share with guys in Krakow as well? Basically, send to all devs
Okay.
when they put in SharePoint so they can watch.
Sounds good.
Thanks.
All right. Thank you guys for your time.
Bye.
Thank you.
Thanks, Josh.
Yep.